Supposedly, we have currently reached a crucial point in mankind's knowledge of the physical universe. After millennia of stumbling awkwardly to explain phenomena, mankind has reduced physical reality to a finite number of isolated building blocks, the components of subatomic particles, whose interactions are governed by a finite number of physical forces and laws. Though the exact character of these components and these laws is unclear, what is clear is that ultimately, from the behavior of these components in the small, we can derive the entirety of the phenomena of the physical universe. The laws of physics, motion, fluid flow, physical chemistry, living phenomena too, are quickly being reduced to complex interactions among these tiny, fundamental components. Even the seeming complexity and variety of human activity is in the process of being analyzed into its organic components. But does this view of science even remotely resemble the mode of creative thought by which humanity has been able to develop consistently over millennia? And if not, from where did this cold view of reality arrive? Let us begin by answering the first of these questions and take a look back to the dawn of modern physical science. The astronomy of the ancients was transformed into the field of astrophysics by the work of Johannes Kepler at the end of the 16th century and the beginning of the 17th century. Whereas astronomers before him had worked meticulously to chart the positions of the heavenly bodies against the nighttime sky, Kepler recognized that it was possible to determine the nature of the physical world, of which the motions seen on that nighttime sky were merely a projection. Because of this, he avoided merely projecting the properties of the visible world onto that invisible world, which lay beyond the celestial sphere. He avoided any attempt to reduce those celestial motions to any sort of mere mechanics. Rather, he looked towards the metaphorical presentation of the idea which must necessarily govern the motions observed.
We perceive how God, like one of our own architects, approached the task of construction of the universe with order and pattern, and laid out the individual parts accordingly, as if it were not art which imitated nature, but God himself who had attended to the mode of building of man who was to be.
For Kepler, because the mind of the creator of the universe was mirrored in the mind of man, any investigation of the physical universe had also to be an investigation of the mental processes which accompanied human creativity. In particular, in his Harmonies of the World, this took the form of a study of the musical relations which the mind of man uniquely recognized. And because man's mind responds to such relations, Kepler recognized the mind of the Creator must also have expressed these relations in that creation itself of which man is a part. Thus, the invisible relations among the harmonies became the principle which governed the visual manifestation of the created universe. This methodological approach gave rise to a completely ordered solar system, which included the discovery that planets moved in almost imperceptible ellipses, whose eccentricities were defined by the musical intervals formed between the planets at their apihelia and perihelia, orbiting the Sun at distances spaced according to the Platonic solids, such that the cube of the ratio of any two planets' average distance was equal to the square of the ratio of their periods, and that the area traversed by the planet in its orbit was proportional to the time required to traverse it. Thus, at the inception of astrophysics as a science, there was no difference between the cognitive capability of the human mind and so-called physical science. This approach disturbed a number of people. One of these people was Pierre-Simon de Laplace, writing later in the 18th century from Napoleon's France.
In Kepler's time, the world had just begun to get a glimpse of the proper method of proceeding in the search of truth, at which genius only arrived by instinct, frequently connecting errors with its discoveries. Instead of passing slowly by a succession of inductions, from insulated phenomena to others more extended, and from these to the general laws of nature, it was more easy and more agreeable to subject all the phenomena to the relations of convenience and harmony, which the imagination could create and modify at pleasure. Thus, Kepler explained the disposition of the solar system by the laws of musical harmony. We behold him, even in his latest works, amusing himself with these chimerical speculations, even so far as to regard them as the life and soul of astronomy. He has deduced from them the eccentricity of the terrestrial orbit, the density of the sun, its parallax, and other results, the inaccuracy of which, now discovered, is a proof of the errors to which we expose ourselves in deviating from the route traced by observation.
Instead of Kepler's approach, Laplace chose to promote the methods attributed to Isaac Newton, who famously declared that he did not make any hypotheses of the sort which Kepler did.
I have not as yet been able to discover the reason for these properties of gravity from phenomena, and I do not feign hypotheses. For whatever is not deduced from the phenomena must be called a hypothesis. And hypotheses, whether metaphysical or physical, or based on occult qualities or mechanical, have no place in experimental philosophy. In this philosophy, particular propositions are inferred from the phenomena, and afterwards rendered general by induction.
Not bad sounding, but what did Newton mean when he said that he did not frame hypotheses? Reports from his closest friends clarify the point. William Whiston, who succeeded Newton in his Lucasian chair at Cambridge, wrote,
"It will not also be unfit with regard to myself, nor unuseful with regard to the public, if I take notice here that during the time of my acquaintance with Sir Isaac Newton, he did always own the impossibility of solving gravity mechanically. And he seemed to me always firmly persuaded that this gravity was derived from the immaterial presence and power of the deity, as it pervaded all the solid parts of the body and operated on them all."
The immaterial presence and power of the deity? That sounds like a hypothesis to me, if not also a metaphysical speculation. If Newton was not really as opposed to hypotheses as he claimed, then what was he promoting with his force of gravity? Another associate of his, Roger Coates, was more explicit in the introduction to Newton's Principia.
He who is presumptuous enough to think that he can find the true principles of physics and the laws of natural things by the force alone of his own mind and the internal light of his reason, must either suppose that the world exists by necessity, and by the same necessity follows the laws proposed, or, if the order of nature was established by the will of God, that himself, a miserable reptile, can tell what was fittest to be done.
That is the exact opposite of Kepler's program. The universe is fundamentally unknowable. Man's reason may be allowed to pursue causes up to a certain point, but ultimately, we must reach the indefinable, the axioms of physics. Just as in Euclidean geometry, solids are said to be composed of planes, planes are composed of lines, and lines are composed of points. But what are points made of? They just are. Since they have no reason for their existence, man's reason is incapable of knowing them.
They simply are. Similarly, it is useless to look for causes in the physical universe. Everything is mechanism, and that mechanism is ultimately reducible to the actions of forces of tiny particles acting in an empty box called space inside of another empty box called time. The human mind is now unnecessary to explain phenomena. The mind is composed of its biology, life is composed of physical material, and that physical material is composed of tiny particles. Therefore, someone like Kepler, who took human creativity as primary, was no more than a mistaken mystic who stumbled across his fundamental discoveries, as Laplace said, by luck. This was the approach which Laplace chose to take. But something curious occurred as he tried to apply Newton's forces to planetary motion. They worked perfectly well when applied to a system of two orbiting bodies, but as soon as a third was added, the equations became intractable, to say nothing of trying to model an entire solar system. In the course of trying to untangle the mathematical knot in which he had ensnared himself, Laplace was forced to invent what was for him a mathematical fiction, a single function from which all of the individual Newtonian forces could be derived. This function, though not known directly, needed to satisfy in every case a specific differential expression which became known as the Laplacian. The function itself later came to be called by Carl Friedrich Gauss potential. What was this potential function? Ironically, after all of the insistence of Newton and his controllers that all of the phenomena in the universe were reducible to and derivable from their component parts, it was being shown, at least implicitly, that Kepler had been correct all along. The individual actions of the entire system could only be explained if the system itself was treated as a unitary whole. The specific properties of this potential function were unfolded by the work of Carl Gauss and Lejeune Dirichlet, and then finally by Wilhelm Weber in direct collaboration with first Gauss and then Bernhard Riemann. But for Riemann, the nature of potential went far beyond that of a simple mathematical formalism, far beyond even the domain of physics itself. Like Kepler, Riemann saw in universal gravitation the manifestation of properties which were otherwise only observable in the processes associated with human creative thought.
We do not, as Newton proposes, completely reject the use of analogy, the poetry of hypothesis, but rather afterwards emphasize the conditions that must be met, and discard any notions that are not essential to the explanation, but that have arisen solely through the use of analogy. With each simple act of thought, something enduring, substantial enters into our soul. This substantial thing appears to us indeed as a unity. However, it appears, in so far as it is the expression of a spatial and temporal extension, to contain an inner manifoldness. Hence, I call this a thought object. The soul is a compact thought object, bound together in the most intimate and most manifold way. It constantly grows by the introduction of new thought objects, and upon this rests its further development. Once formed, the thought objects are imperishable, their blending indissoluble. Only the relative strength of their unions is changed by the addition of new thought objects. Thought objects require no material carrier for their continued existence, and exert no lasting effect upon the world of phenomena. Thus, they stand in no relation to any part of matter, and consequently have no position in space. On the other hand, all beginning, generation, all formation of new thought objects, and all unification of the same, requires a material carrier. Hence, all thinking comes to pass at a determined place. Thought is a process within ponderable matter. Our external experience, the facts of our external perception, which must find their explanation in the processes within ponderable or gravitating matter, are 1. Universal gravitation, 2. The universal laws of motion. Something lasting underlies each act of thought, something which, however, is manifested only under the specific occasion of memory as such, without exerting any enduring influence upon phenomena. Therefore, with each act of thought, something lasting enters our soul, something which exerts no enduring influence upon phenomena. On the other hand, our external experiences about ponderable matter can be explained if it is assumed that a homogeneous substance fills the whole of infinite space and constantly flows into ponderable matter and vanishes.
Riemann's approach was to take creativity per se as an object of experimental study, and to apply the workings of the mind of man in order to understand the mind of its creator, whose mind in turn lay behind the functioning of the physical universe. Riemann's clear rejection of the mechanistic fallacy of Newton and Laplace made possible his most crucial discoveries in physics. As we have heard from him here, and as he himself says in his groundbreaking habilitation dissertation on the hypotheses which lie at the foundations of geometry, it was a direct study of the creative processes of the human mind which led him to the discovery that space and time were not self-evident existences. This recognition was what made Riemann uniquely capable of inventing the mathematical language which later became necessary for the formulation of Einstein's general theory of relativity.
But if all modern science depends upon these discoveries of Riemann, which resemble more the approach of Kepler and Plato than of Newton, how can it claim to have reduced those creative faculties of the human mind to the mere behavior of subatomic particles? Perhaps the picture which modern science presents of the universe is nowhere near as complete as it seems.
In fact, the view of science which was promoted by Kepler's detractors was riddled with conceptual holes. This was recognized by, among others, the great scientific minds of Max Planck and Albert Einstein. Planck saw in the atom the same problem which Kepler had recognized in making the leap from astronomy to astrophysics. The world of the atom, like the organization of the solar system, was not directly accessible to human sense perception. Instead, the paradoxical projections of this invisible domain onto the separate senses of vision and hearing needed to be investigated to reveal their underlying harmonic character.
Can such a deeper conception of science be the basis for a guiding philosophy to live one's life by? We find the surest answer to this question by looking back in history to the men who embraced such a conception of science as their own, and for whom it indeed served this purpose. Among the numerous physicists for whom their science helped them endure and ennoble a miserable life, we remember, in the first rank, Johannes Kepler. Outwardly, he lived his life under beggarly conditions, disappointment, gnawing hunger, constant economic pressure. What kept him alive and able to function through it all was his science, but not the numerical data of the astronomical observations in themselves, but his abiding faith in the power of a lawful intelligence in the universe. One sees how significant that is in a comparison with his employer and master, Tycho Brahe. Brahe possessed the same scientific knowledge, the same observational data, yet he lacked the faith in the great eternal laws. Thus, Tycho Brahe remained one among many worthy investigators, while Kepler was the creator of the new astronomy.
This resistance by Planck to what became the insane formulations of quantum mechanics was communicated to his student, the psychologist Wolfgang Köhler.
The physicist likes to give this impression a disturbing touch. The pavement, he would say, on which you walk along the street, is for the most part empty space. In so much emptiness, tiny electric charges rush about here and there, and it is only the ever-repeated impulses of such charges which keep your feet, and all the rest of you, above the ground. When a physicist tells us that a macroscopic object is really a swarm of particles, do we understand him correctly if we assume that atomic physics does not recognize the existence of definite macroscopic objects? Are macroscopic objects dissolved into particles? At first, it might appear as though only one aspect, either the microscopic or the macroscopic, could correspond with physical facts. And yet there is no such alternative. Both the demarcation of macroscopic objects and their atomic constitution are legitimate notions which are well founded on physical evidence. Particles do occur as separate entities. They are also real parts of macroscopic objects. But functionally, they are not quite the same entities in the second as in the first case. And we still trust the particles themselves more than their fields, as though, in the case of the pavement, we could safely tread on particles but should beware of mere fields. As a matter of fact, insofar as particles are known to be fields and field structures, they fill the volume of a macroscopic object completely. It is only as a field continuum that it coheres. And the support which the pavement gives to our feet is entirely due to this continuum. It will not yield unless much stronger forces than our weight are applied.
Köhler was trained extensively in the German classics, which for him included the work of Riemann and Weber, as well as that of Bach and Beethoven, but not, for instance, Wagner. This standpoint allowed him also to recognize that the paradoxes of quantum mechanics were only pseudo-paradoxes, logical consequences of a fallacious worldview which rejected the factual existence of human creativity as an independent driving principle in the universe. Köhler and his collaborators identified the fundamental unit of human thought as the Gestalt. The German word Gestalt means form or shape. In the psychology of Köhler, it indicates that what is recognized by the human mind is never a collection of individual sense impressions, but rather a whole, which is, in a certain very specific sense, greater than the sum of its parts.
In Gestalt psychology, we distinguish three major traits which are conspicuous in all cases of specific organization or Gestalt. Phenomenally, the world is neither an indifferent mosaic nor an indifferent continuum. It exhibits definite segregated units or contexts in all degrees of complexity, articulation, and clearness. Secondly, such units show properties belonging to them as contexts or systems. Again, the parts of such units or contexts exhibit dependent properties in the sense that given the place of a part in the context, its dependent properties are determined by this position. May I use an old example once more? A melody is such a context. If it is in A minor, for instance, minor is a property belonging to the system, not to any note as such. In this system, the note A has the dependent trait of being the tonic with its static quality. We can analyze the melody, but not in independent parts. That would be destruction of the melody. Its minor character, for instance, would be lost.
This obvious fact of human creative thought is evident in all forms of classical composition and forms the basis of the mind's ability to communicate and receive profound ideas, as opposed to just a string of sense impressions or information. Its existence was frantically denied by reductionist psychologists in Curler's day, who instinctively saw it as a threat to the political philosophical worldview which they were promoting. Nonetheless, said Curler, the Gestalt is a scientifically verifiable fact of human creative mentation, even of human sense impression. Moreover, said Curler, this phenomenon in the human mind must necessarily have corollaries in both physics and biology, if only because it is through the human mind, and only through the human mind, that we are able to arrive at the truths of these sciences. In biology, this was most clear. Life could be reduced to non-living parts, just as a musical line could be reduced to its component notes, in the first place by killing the organism, and in the second place by killing the musical idea. But the living organism qua living organism was more than the sum of those parts. In fact, a newly dead organism consists of exactly the same parts as the living organism which it was just a moment before. Many embryologists, such as Hans Driesch, were well aware of the fact that the growth of the living organism was impossible to explain mechanistically. The pattern of growth and development of a living embryo unfolds as if with the final stage of its development already in sight. This concept was developed by subsequent thinkers such as Hans Spemann, Ross Harrison, and Alexander Gurvich into the concept of the morphogenetic field, leading them to apply to living processes the same concept which had earlier been applied to universal gravitation, the idea of potential. Some of these thinkers, including Curler, took this a step further and recognized what Riemann had already recognized several generations earlier. The concept of potential represents a physical gestalt, a single idea from which an infinite number of individual forces could be derived, in the same way as points can be derived from the intersection of bodies. But that single idea was in no way composed of those individual forces, any more than bodies are composed of points. Returning quickly to this geometric example will provide us with the conceptual material necessary to understand this point. The intersection of two bodies forms a surface. Since this intersection can occur at any location within the body, we are compelled to say that the body is composed of these surfaces. But let's try the inverse. Let's try to actually construct a body from surfaces. Now, a plane is that which has zero height. Therefore, no matter how many of them we stack on one another, we will never be able to construct a solid body. That is, 0 plus 0 equals 0, no matter how many zeros are added. In that sense, we may say the geometric body is more than the sum of its parts. Or, put perhaps more accurately, we say that the surface, the line, and the point, that is, the parts, do not actually exist as independent entities. They are simply derived as singularities within the otherwise continuous whole.
Leaving now the domain of geometry, let's return to the physical world and see where this inversion of the reductionist analogy takes us. We see now why Laplace was unable to derive the supposed individual forces of the solar system until after he had first been forced to conceptualize the entire process as a whole, that is, as a gestalt, though he was incapable of recognizing the significance of what he had done. We also begin to see the fallacy of the reductionist attempt to define the atom as independent of the phenomena of life and cognition. The atom per se is a fiction. It does not exist independent of the process in which it is found, any more than a point exists independent of a line.
Thus, in order to fully understand the science of potential, we must first begin to understand the nature of Gestalt. This brings us permanently out of the domain of so-called pure physics and into the domain of human creative thought.
When reading the formulae of the physicist, one may emphasize this or that aspect of their content. The particular aspect of the formulae in which the Gestalt psychologist became interested had for decades been given little attention. No mistake had ever been made in applications of the formulae, because what now fascinated us had all the time been present in their mathematical form. Hence, all calculations in physics had come out right. But it does make a difference whether you make explicit what a formula implies or merely use it as a reliable tool. We had, therefore, good reasons for being surprised by what we found, and we naturally felt elated when the new reading of the formulae told us that organization is as obvious in some parts of physics as it is in psychology. Incidentally, others were no less interested in this new reading than we were. These other people were eminent physicists. Max Planck once told me that he expected our approach to clarify a difficult issue which had just arisen in quantum physics, if not the concept of the quantum itself.
The concept of the quantum, of atomic science itself, is intimately tied to a study of the creative processes of the human mind. The phenomena in the small must be studied as derived from the cognitive phenomena in the large, and not vice versa. What new frontiers for science this opens up! Instead of trying desperately to build a bigger and better machine to smash dead atoms, we must devise new experiments which will shed light on the nature of subatomic phenomena within living processes, which will involve a return to the morphogenetic field studies of Gurvitch and others. As a corollary, we must, like Kepler and Planck later, discard any attempts to describe phenomena in the very small using a language borrowed from the visual domain of macroscopic objects. Instead, a harmonic approach must again be taken, where the evidence of gestalts in both hearing and vision must be taken from the cognitive domain and applied to phenomena in the very small. Molecular biology, quantum mechanics, genetics, neuroscience, cognitive science, these are reductionist studies which must take a back seat to true scientific investigation. Further, the frontier research areas for the examination of such gestalt phenomena must become such fields as classical musical composition and a study of classical poetry and prosody which is free from the reductionist trends of modern linguistics. But this study of human behavior in the large points to an even broader science of human creative activity, that of physical economics. Physical economy, properly understood, is not the study of flows of money or even physical goods. It is rather the study of the macroscopic organization of human creative thought. This anti-entropic growth of the human species, by which the physical universe around us is brought more and more into explicit conformity with the reasoning processes which underlie it, is, in fact, the model for all sub-processes within it. Animal evolution, for example, is simply a more diluted and drawn-out form of the type of conscious evolution of which the human species is capable. Only studies which contribute to this conscious evolution, bringing man in his physical expression closer and closer to the cognitive potential which is implicit in the universe as a whole, are actually deserving of the name of science.